When most people look at a building, they see walls, windows, maybe a nice paint job if the contractor didn't cut corners. But what they don't see, what almost no one thinks about, is the invisible story of how that building holds itself up. Because everything around you right now, from the chair you sit on to the roof above your head, is part of a quiet negotiation with gravity. And gravity does not take days off. So today on Deconstructed Build, we're going to follow the weight. Literally, we're going to trace the exact journey that every kilogram, every pascal, every kilonewton travels from the roof all the way into the ground. And along the way, you'll start to see why buildings are designed the way they are, why engineers argue so much, and why even a tiny mistake in this invisible chain can lead to catastrophic failure. Every building begins with loads, forces. Some are predictable, like the weight of the roof, the floors, the walls, the beams, the furniture, the finishings. Engineers call these dead loads. They don't move, they don't change. They quietly exist. People moving inside the building, heavy equipment rolling across a slab, wind pressure that pushes and sucks, a room full of students jumping during a TikTok dance. These are live loads, and the building must accept them whether it likes it or not. And then there are loads that buildings dread, like earthquakes, which don't just shake the ground but twist the structure. Or cyclonic winds in places like northern Australia and the Pacific, where gusts can pull a roof upward like it's made of paper. But all of these forces, predictable and unpredictable, must be guided. And the way buildings do this is not random. It's a system, a chain, a path. Imagine rain pounding on a roof. The roof sheet collects the weight, but the sheet is too thin to carry anything serious, so it transfers the load to the battens or purlins. Those purlins hand it over to the rafters or beams. And those beams don't want to carry all that weight alone, so they look for support, usually the nearest column or load-bearing wall. Think of it like passing a heavy box across a crowd. Each person handles a bit, then hands it to someone stronger. Floors work the same way. The slab or floorboards carry the load of everything on top of them. But they don't hoard that weight. They spread it to the beams beneath. The beams then feed that load into the columns. This process, from wide surfaces to more concentrated members, is the first part of the load path. Broad to narrow, distributed to concentrated. By now the building is saying, okay, I've gathered all this weight. Now, where do I put it? Columns are the workhorses of most structures. They're designed to take all the loads coming down through beams and deliver them vertically. The funny thing is that people often think columns hold up weight. That's only partly true. What they're really doing is transmitting weight. If a beam is like a courier, the column is like a freight elevator moving everything downward. And here's where things get interesting. Columns don't just carry raw weight. They also handle eccentric loads, moments, and lateral forces. If a column gets overloaded, it doesn't just crack, it buckles. It gives up in a sudden, dramatic way that structural engineers pray never happens on their project. The size of a column, the rebar inside, the grade of concrete, none of that is randomly chosen. It's mathematically tied to the loads coming from the roof and floors. If you increase the live load upstairs, your column may suddenly require twice the reinforcement. So when people ask, why is that column so thick? The answer is simple, because the building said so. By the time the load has traveled through beams and columns, the building has done all it can. It has gathered its own weight and the weight of everything inside it, and it now reaches the point where it must hand all of that force to the only thing big enough to handle it. The earth beneath it. This is where foundations step in, and honestly, they deserve more respect than they're given. Most people see foundations as blocks of concrete buried in the ground. But foundations aren't there just to hold things up. Their real job is far more delicate. Foundations take the intense, concentrated forces coming from the columns and spread them into the soil in a way the soil can actually bear. It's like stepping on snow. Barefoot, you sink. But wear snowshoes and suddenly you're floating on the surface. A foundation is the building's snowshoe. It spreads the weight wide enough so the ground doesn't collapse beneath it. And the type of foundation chosen for a building isn't some random tradition or contractor's habit. Each one exists because of specific soil behaviors, structural demands, cost realities, and design philosophies. Take isolated footings, for example. These are the compact individual footings placed beneath each column. They're the simplest and most economical option when the soil near the surface is strong enough to carry the load. They're perfect for small to medium buildings where loads are moderate and well distributed. But even they have rules: the size of the footing, its thickness, the reinforcement pattern. All must be carefully calculated based on the soil's bearing capacity and the column's load. If the building uses long masonry or concrete walls that carry load continuously, isolated footings don't make sense. So engineers turn to strip footings, long, continuous footings that run beneath the wall. These aren't just longer versions of isolated footings. They behave differently. They spread the load over a wider area, they resist bending along their length, and they help keep long walls from cracking due to uneven settlement. Then there are raft foundations. These are the big guns of shallow foundations, a massive slab that sits beneath the entire building, distributing load across the whole footprint. Engineers bring out rafts when the soil is weak, or when loads are spread out over a large area, or when differential settlement would be too risky with individual footings. Rafts act almost like boats. They float the building over soft soil, spreading weight evenly across the entire surface. But when the soil close to the surface simply cannot be trusted, maybe it's too soft, too saturated, too deep with organic material, or simply not strong enough, then shallow foundations are off the table. In those cases, engineers go deeper, literally. Piles are driven or drilled downwards until they reach soil or rock strong enough to carry the structure. Some piles work through friction along their length, others rest directly on solid strata, and many do a bit of both. But the principle remains: when the ground above can't carry your building, you reach down to the ground that can. This is why a foundation is not just concrete. It's a negotiation between the building and the earth. And like all negotiations, things can go wrong. Despite centuries of advancement, despite endless calculations and layers of codes and standards, foundations still fail. And when they do, the building rarely whispers, it screams. One of the most common reasons for failure is poor soil investigation. A building's behavior can only be predicted if the engineer truly understands the ground beneath it. Soil investigations are more than drilling a few holes and sending samples to a lab. They are geotechnical detective work. Engineers evaluate soil layers, measure moisture content, test density, check for expansive clays, identify weak strata, locate water tables, and try to understand how the soil will behave not just today, but 20 years from now. If that investigation is rushed or ignored, the entire building becomes a gamble. Foundations can also fail simply because they're the wrong size. If a footing is too small for the load it carries, the soil beneath becomes overstressed. It compresses. The footing sinks. And when one part of a building sinks more than the rest, you get differential settlement, the silent enemy of structures. Walls crack, floors tilt, doors jam. And in the worst cases, the entire structure becomes unsafe. Water is another enemy. A rising water table can reduce soil strength. Heavy rain can wash away fine particles in sandy soils. And swelling clays, especially in tropical and subtropical regions, can expand with moisture, lifting foundations upward or shifting them sideways. Reinforcement errors inside the foundation are another hidden cause of failure. Concrete is strong in compression, but weak in tension. Rebars exist to carry that tension. If the bars are the wrong size, poorly spaced, or improperly placed, the footing becomes brittle and can crack under load. And sometimes the issue isn't the foundation or the soil, it's the building owner. When floors are overloaded with heavy machinery never accounted for in the design, when an extra story is added illegally, when the building is used differently than allowed, even the best foundation can fail under loads it was never designed to bear. All of these problems sound different, but they trace back to one truth. A building is only as strong as the soil it stands on, and the soil is only as strong as our understanding of it. Now, this may surprise people outside the industry, but the soil is not just the supporting actor, it is the true backbone of the entire structure. Everything else you see above ground is simply a well-organized effort to deliver weight to the earth. If the soil is too soft, the building sinks. If it's too wet, it loses strength. If it expands, it cracks concrete. If it erodes, it undermines support. If it's not compacted, the building will never sit evenly. So when engineers drill boreholes, take soil samples, run Atterberg limit tests, measure water content, perform SPT or CPT tests, and classify layers, they're not doing it for fun. They're trying to answer the most important question in construction. Is the ground ready for what we're about to build? And if the answer is no, they either improve the soil, redesign the foundation, or change the entire building strategy. Because gravity does not negotiate. A building is a conversation between structure and soil, between forces moving downward and resistance pushing upward. Every mistake in that chain accumulates. Every success compounds. And the more we understand foundations and soil, the more we understand buildings themselves. That is the real story of the load path, not just beams and columns, but the invisible handshake between human engineering and the earth beneath it.